Just take a seat wherever you want. Hi. So yeah, in this demo, I'm just going to show you the photoelectric effect with a simple device called the electroscope, which basically it's like a home-built device that I'm going to show you as I speak. So it basically consists of these very thin aluminum structures, and then they are connected by a copper wire, and then the copper wire sort of suspended using this cup. Feel free to place the things in front. Good one. I think you can just share with your neighbor. Yeah. There's only one for it? Yeah.
Now, here's just a cup, and you can, this is the zinc tank, you can put it on it.
You need two of them to make it electric. Be careful, like don't bend the aluminum. Yeah, just connect them with the same wire. Yeah. And then you put the metal sheet on top of the wire for electrical contact. Okay. So the way it works is like this. So I'm sure that you are familiar with the concept of static electricity, right? So when you, let's say, you rub a rod with some, let's say, your hair or your clothes, and then it sort of induces some charge on the rod, right? This happens mostly in dry weather, especially in the winter, and that's how we sort of do that. We basically rub it with our hair, and we transfer some charge here, and then we bring this very close to this. So this induces some opposite charge on the plate, and because this is a metal, the whole thing gets charged, and your leaves also get charged. And now if you have metal with the same charge, they start to repel each other, electrical repulsion, and then your leaves sort of open up, right? And then what you do is, how do you make the leaves? So when you like take your things off, then your charge is sort of like dispersed, right? And your leaves will close. How do you make your leaves permanently open? So what you do is you touch this thing with your finger. By doing this, you basically ground the whole thing, and then charges sort of travel from the leaves to your finger, and then you remove your finger, and then you remove this. So the whole thing gets some charge, overall charge, and the leaves sort of permanently open. And that's how the electroscope works. And then I'll show you how you sort of make the leaves close again. Let's just using the photoelectric effect. So you sort of do this. You do this with a fur, rabbit fur, or you can use your hair if you want. I don't have hair, so I can use it. It closes, right? If I remove it, it closes back. So how do I make it permanently open? I have to ground it with my finger. It closes. Take my finger off. Take this out. It opens. And it stays open because this whole thing is not charged. It's like this case. Yeah. Right there.
If you touch it, then it transfers the.
You move your finger out first and then pull out the rod.
Otherwise, it would be neutral again because your cell is like an infinite amount of electron supplier and receiver. So if you keep your finger on it, it will just try to be like neutral.
So, question, what are the applications of the photoelectric?
That's a good question. One of the biggest application is the solar electric, like the solar light on the solar plate, it will generate electricity. That's the like majority amount of where electricity comes from nowadays. Just from this photoelectric effect. It's called and we didn't introduce the photoelectric effect right now, but we will do it.
Yeah.
Right now it's just some ENM.
So
Yeah,
like
physics
static electricity.
knowledge. Yeah.
Electric.
Yeah.
So yeah, now it's where the photoelectric effect, quantum effects come. So now that the thing is has some overall charge, I want to make it discharged, right? So I basically have to knock off the electrons of this metal. To do that, and so as you know, metals have atoms in them. Atoms have a positively charged nucleus, and then the electrons are sort of traveling around the nucleus in fixed energy orbitals, right? And to sort of knock the electrons off the metal, you need to supply that fixed energy or more, right? So if let's say I shine some light to the metal that doesn't have that energy, no matter how strong that light is, no matter how let's say I shine let's say a billion photons on this that doesn't have that energy, I will still not be able to knock the electrons off. But on the other hand, let's say I shine in just one photon that has that energy, I will be able to discharge the metal. So that's why the quantum things come in. So light consists of discrete particles called photons that have fixed energy, and that fixed energy will interact with your electrons, and it can lead to ionization. And that's the photoelectric effect. So this is zinc, and zinc sort of works like to ionize zinc. You basically need to use an UV light. It doesn't have to be a very strong UV light, but on the other hand, let's say I use some red light, which doesn't have that energy. No matter how strong that light is, I won't be able to ionize it. So here's going to show put the UV light on this, and I'm going to use this thing and see whether. So this is like a more sophisticated version of the electroscope that you built. So this is already charged, and these things are repelling each other now, and I'm gonna like use this to see whether I'm able to discharge it. It's pretty strong. I can hold it for like eternity, and it won't close. But
the top plate is zinc.
yeah. The top plate is zinc. It's just coated with a different color. That's why it's yeah.
You can also try your cameras.
You can try with your cell phone flashlight if you want. It's like white light. It has must be.
Yeah, it's fine. I'm going to show you how the UV light shine on this. See? And this is supposed to work for all of your devices. All the electroscope you just did.
So why UV light and not regular flashlight?
Yeah,
That's what it's saying, right? So UV light, it has its photon that has a particular energy. It has like, so let's say if you're, this electron has an energy, right? And your UV light has that energy just enough to knock the electrons off. And if you have, let's say, a red light, it doesn't have that energy. It won't be able to knock it off.
Is there any material that we can do this with invisible light? Any frequency?
I don't think so.
I think for the majority of the metal,
It's
material,
mostly-
it has to be some UV, above UV. So this is some phenomena was was thought by scientists at about 1896. They just saw that if some UV light shine on metal, there will some electron will appear, but they don't understand why. Until Albert Einstein explained this as, oh, this is actually the quantum effect. You need to treat the light as photon. This is the key part of why it's quantum, because you have to treat the light as photon. If you treat it as a continuous wave, it doesn't work. It cannot explain why if you keep shining the red light high enough intensity, like forever, it will not, the electron will not go. You have to shine a light with enough frequency. You need to treat it as photon, and the energy for photon is the H time constant times the frequency. And electron accept that energy and keep out from metal. That's the key part. That's the key point of why this is quantum, but not classical. Thanks to Albert Einstein. And yeah, you can try to charge your own devices, and we can bring the UV light to this charger. Yeah, you can. Feel free to use any of. Oh my God, so sorry about that. And feel free to use this microscope, and then yeah, we have more of the rabbit fur. And this black this material is used to rub the zinc plate so that you can remove anything above it, like letting it to be pure zinc. There will be some oxide on it. If the UV light cannot discharge it, it is because of this. Yeah, I think the charge on it is not enough. Yeah. You can try to use your camera's light to shine on it. First you try it. Yeah, this experiment has some limitation. One is the humidity. The humidity of this, like today's humidity is just too high to make the electron as much as what it can be if in the winter. If in winter, this experiment would be super good.
Why does humidity?
Oh, it is because the water vapor in the air will extract electron. Like it's like the whole air is ground. You are automatically lose electron to the air, so it cannot get as charged as it is in the dry air. The rabbit fur is always the best choice for get some charge on it. Yep. Just try to use your phone light or some other kind of light, not UV, not above UV, not gamma ray, not X-ray.
If you had cameras, I'd be very concerned. And just carrying around some like radioactive material. At all.
What's some high-level applications of this?
Your like solar cells.
Okay.
That's one of the biggest things. And also this sweet demo that can present not in the lab, not in research, but in daily life. You can just make this in your home. I think the most dangerous part is UV light because it might hit your skin, your ear, but all the other parts is just cheap and easy to build.
So you mentioned one application was like photovoltaic cells, but humidity played a big factor in how effective that was. How do you, I guess, mitigate those issues?
Oh, that's like humidity is a problem for this experiment. But there's there's a normal type of photoelectric effect is that you have a vacuum cell and you have a metal plate here. And here it is just a circuit. They just shine the light on this plate. And because this is vacuum, there's no charge. My bad, there's no vapor, there's no water vapor in it. And the electron will it will always like fly away from this part to here and forms the current. I think the same things happen when you have the solar plate. You just create an environment that there's no ground, there's nothing can dissipate the charge to somewhere else. And then as long as the electron on the plate is kicked out, it will go into the loop and form a current, and there will be electricity.
As long as there's nowhere else you're gonna see.
Yep.
So that's the principle of the solar cells, is it like, does it also use the UV radiation that gets through the atmosphere?
The solar light has UV.
Yes, yeah.
Yeah. It
And
is.
then those just kind of excite the electrons, and those electrons just
Goes into
produce
the
electricity.
goes in circuit.
Can we pass around the?
Yeah. Here. Yeah. Let me try to neutralize it first.
And we must give it a try. It's neutral now.
Can I go over this one?
Yeah.
Yeah, this is the best
Can I
combination.
try some?
Like this two. And we can also bring the UV light here for. It's too sharp. Yeah. I think in there is.
Yeah, you gotta like really get it charged for it to work.
Let's do that.
Yeah, we're
It's
doing
very
it.
long.
It's not a winter day. If it's a winter day, then only a few times should be good. You need to
Alright,
charge
so
it.
don't touch the rod and use your finger to discharge.
Yeah, because your
Touch
cell
the
is
plate
it's like
and then
round.
Keep
move
the
your
rod
finger.
closed. Okay, and
Remove your finger. And then the rod.
Move the rod.
Now
Yes.
it's sort of permanently charged there.
You said sort of.
Because of the humidity.
Yes.
Yeah,
exactly.
water.
Yeah.
So eventually, because of the water, it will slowly go back.
Yep. And you can try to use your phone light to shine on it. Nothing.
How long would that take?
It would not happen.
It's just not due to the quantum, due to the energy.
It has to be the frequency.
Above, below.
No, you said
The water
sort
part.
of permanent, but they'll
Oh,
eventually dissipate because of the
it
water.
depends on humidity. If humidity is super high, it will just get discharged very fast. But if it's like in winter day, I think it can keep for a week or longer than that. Yeah, I guess.
I think
But if it was in vacuum, theoretically, it would stay charged.
Yeah.
With the UV light, it shows pretty
I think it's mine.
Oh.
Sorry about that. Thank you. Okay. I don't want shiny for
Yeah.
longer time because it's kind of dangerous. You can already smell something. I think that's ozone because it's trying to ionize the
Because this has ozone in it, right?
Huh?
This lamp has ozone inside it. That
Really?
yeah.
Like in the tubes.
In the tube. That's the thing that works.
So yeah, just feel free if you have any question, and you can play with your own like your handmade aluminum foil. Yeah. That can also be reclosed. Like once it's open, it can be closed with the only the UV lights.
We're a couple minutes ahead of schedule, so yeah,
Yeah, just
we can mess around a bit more. And, yeah.
Alright, so we kind of work with atoms and
Get those, get the rod.
we try to use laser light to cool
So
atoms.
there should be a
Yeah.
separation between. So originally, the electroscope was used
Oh,
to see
so
how much charge
Same.
and the angle between the leaves showed
Basically the same.
how
Not the same.
strong the charge
Same.
was.
Where do
So they used gold leaves because they were so
Gold
thin
atoms.
and light.
Rubidium
Gold leaves,
Oh,
that was very useful.
because it's cold, right? So that's why we call it cold.
But they found out that if you shine a strong light laser on it, it goes away. That's why Einstein always stresses light's not arbitrary.
How it's different from their experiment? So I think what they do is they basically cool their atoms to as cold as it can get. It's called a Bose-Einstein condenser. And we do it differently. We don't code it as much, but we sort of excite it to a very high energy state. It's like when you have the electron there, it's almost ionized, but not completely ionized. So it's a very high principal quantum number. And when you excite the electron to that level, your atom sort of gets a very large. Are you familiar with dipole moment? Like it's like if you have like very excited atoms that are brought close to each other, they start to attract a lot. And that so it's like long range interactions. So and that long range interaction can be used for a lot of things. Like it can be used in quantum computing. And there are also other interesting things. Yeah, we try to work on that.
So
Your body now has tissue. But it's not a lot of charge here.
yeah.
What is cooling and exciting? I'm guessing cold atoms.
Yeah, our lab is code atom experiment. Oh, are doing code atom experiment? Like you mean how coded it is?
Yeah.
Oh, it's
Very very cool. It's like microkelvin.
one e to the negative 10 times power of negative 6.
The previous demonstration we did the optical lens lab where the previous
Kelvin.
demonstration.
Oh, yeah.
So that was like nanokelvin, right?
Yeah.
And this is microkelvin.
Yeah.
So microkelvin is a million, and then nanokelvin is a billion.
There's a microkelvin how to excite the electron to higher energy.
Oh.
Is it because of the temperature, or how do you excite it?
We don't excite the electron. We excite the atom to excite the state.
Right.
We are playing with the rubidium atom, and we just shine the laser on resonance with the energy level, so it get excited.
Oh,
to
yeah,
the state.
yeah. You don't excite the photon.
Yep, the photon.
Yeah.
Light matter interaction.
You say what applications of it?
Oh, for this application, you don't need a code atom.
For the
Oh.
lab.
For this, there are a lot of applications like the quantum information, because they are very cold, and so you just do quantum computing like the qubit.
Yeah.
So like you can think of temperature as some kind of disorder, right? So the colder you get, you have less disorder. You have your atoms are very clean,
Yeah.
and so that's why you can sort of do quantum computing, quantum information. If you basically, let's say you have a sealed glass with a lot of atoms inside, your atoms are always like colliding with the air inside, colliding with themselves. You cannot really do this experiment carefully. But if your atoms are cold, so basically our experiments are all done inside a vacuum chamber, like ultra high vacuum, like very, very, very pure vacuum. So there are basically no collisions with the background gas, with air. And so that's why, so that's the reason why we pull that out.
Alright, round of applause, please. We move on to, we have a short break, if you guys need the restroom, or just roam around for like, be talking for outside. And we can go to the next one. Two.
I think it depends. There are just some communities use cesium, use rubidium, use like helium, just like, and the company need to build a laser for us. They need to build a laser that has a specific wavelength to send it from ground state to send the first level state and then to the higher level state. So it's about, I think it's about community. They already have this well-built components. Like how to, where do we get our rubidium atoms from a what's that called? It's just from it should have some source of the atom. They just have everything built up for you. You can use it for its own way.
People mostly use atoms that are heavy. Rubidium is not heavy. you cannot. It's very hard to pull, let's say, or even helium because they are light, so they move a lot. So you can basically think of pulling atom as stopping the motion, right? The lighter the atom is, the more likely it's to move. The faster it's going to move. You basically stop the motion, right? So that's why we usually cool heavy atoms. And the reason why we cool metals, like atoms that are on the left side, is because just because of their electronic structure. It's just easier to cool atoms that are on the left side as opposed to, let's say, zinc or oxygen.
You wanted to cite the kind of the big dipole moment, right? To make like those long range interactions.
Yeah.
So what is the point of the interaction?
So like let's say you have if let's say two atoms interact a lot, you cannot bring the two atoms close to one another beyond a certain distance. Because if you do that, they're going to just collide with each other and just like fly over or just get destroyed. So you basically what you do is you basically have, let's say in your experiment, you can only have your atoms at certain places. That can be used as a tool to study quantum mechanics. You can sort of like move your atom from point A to point B in a predicted manner. And you can sort of use it to, let's say, most like Hopping, yeah.
Another thing is like because they have large interaction, which means if you have one exist, like one excited point exists there, the other one will be suppressed, and this will create some kind of non-linearity. And non-linearity is like you have in the quantum information you have 1 0. It's like you can use that for the 1 and 0 for the basic. That's another application. Yeah, and the existence of one will suppress the other zero because of the not there's no tangle, there's only the dipole element. It's only because of the interaction. The energy level is shifted because of that long range.
So one is one, the other can go.
Yep, it's like control qubit. One is there, the other one has
Oh, you use that for
yeah.
But all these
Yeah.
I think now they all are like very close because for the superconducting quantum computer, it also needs to be superconducting for superconducting to happen. And for in our community, we are actually the neutral atom community. There's and I think another community is the ion community. Is ion the trap ion, yes, but we all need to be close to prevent the decay disorder and bad things happen. Just we are all fighting for education. All these communities are fighting.
Thank you.
Thank you. Okay.
We're gonna skip this. Whatever.
No.
One guy. You can look around. Any questions? So I'm the